So we'll continue discussion on this one. And first I will share the screen. Yeah, everybody able to see this screen?
Yes, sir.
Okay. So just revise what we had discussed in the last class. So what we are looking at, we want to find out the uh, intersection of given line segments. So n line segments are given to us. We want to find out the intersection points between them. And for the sake of simplicity, we assume that actually the endpoints of these segments are distinct, and each and every intersection point is defined exactly by two segments. That means actually no three lines segments intersect at the same intersection point. And we were discussing about the sweep-line algorithm, and sweep-line algorithm is nothing but we are visualizing our imaginary horizontal line is sweeping the plane from the top to bottom, and in the process it crosses the top end points of the some line segments and bottom end point of the line segments and intersection also. So in the process, whenever the sweep line crosses the intersection points, we want to report them. So in order to do this one, so what we have seen actually is we don't want to test all pairs whether they're intersecting or not to get a output sensitive algorithm. So in order to avoid testing some line segments pairs, so we want to use this something close to each other should be tested whether they're intersecting or not. Something which are very far from each other, we don't need to test. And we have seen that X overlap and Y overlap plays an important role. And two line segments having a X overlap, Y overlap, there are a possible candidates for intersection. We will see whether they are intersecting or not. So to capture this one, what we have came across is actually sweep line algorithm. So when the imaginary horizontal sweep line is sweeping from the top to bottom, at any given instant time, the line segment sweep line intersect the some line segments. So we maintain the left to right order of the line segment intersected by the current position of the sweep line, okay, as its status, sweep line status. So we are maintaining the left to right order of the line segments as a sweep line status. We are not maintaining the intersection point, but only we are maintaining the sequence of the line segments. Of course, this sweep line status changes when it moves from the top to bottom. Of course, this status is not changing continuously, but status is changing at some finite points. Those we are calling as a sweep line events where the sweep line status changes. So those are the top end point of line segments where whenever the sweep line crosses the top end point, then sweep line status changes. Okay. Similarly, when the sweep line crosses the bottom end point of any line segment, then sweep line status changes. Similarly, whenever it crosses the intersection point, then also sweep line status changes. So these are the events: top end points, bottom end point, and intersection points. And initially, we know that top end points and bottom end points is given to us, but we don't know the intersection points. Of course, our objective also to find out the intersection points. So In the process of sweep, we find these intersection points and we'll report them, and we also treat them as events to update the sequence status. So we do this on the fly. So algorithm goes like this. So initially the sequence status is nothing, empty, initialized to empty, and the event queue. Okay, we are actually maintaining all the known events till now, the top endpoint, bottom endpoints, because we don't know the intersection points. So we process this event from the top to bottom. That means the events which are having highest y coordinate with higher priority, and use that actually in the event queue maintenance. So we are extract the minimum from the queue, and if the top endpoint, and we insert this line segment corresponding to this event into this sequence status, and we check whether this new segment which is inserted is intersecting the segment which is left of it and right of it or not. If they're intersecting, we'll find the intersection point and insert into this event queue. That's what we are doing here. Similarly, when this next event is a bottom end point, okay, we'll simply remove this line segment, okay, whose endpoint is what we are current event, and by removing this one, so new segments which are either side of this event segment, this and this, becoming adjacent to each other, and we simply check whether intersecting or not. If they're intersecting, put this into event queue. Similarly, when this sweep plan crosses the intersection point, I will simply report this one and update the order of this segments in the sweep plan status. So by changing the order, and this are becoming adjacent, we'll check whether they're intersecting or not. If it is, then we simply insert into event queue. Similarly, other two pairs also we check, this two also. So if you look at this one, if you use the appropriate data structure, okay, and these insertions and finding the left one, right one, okay, can be done in logarithmic time. So each top endpoint can be managed in logarithmic time. Similarly, this event queue also, inserting this event into the event queue also can be done logarithmic time. So to handle one top endpoint, we need a just logarithmic time. Similarly, bottom endpoint also can be handled in logarithmic time. Okay. Yeah. Similarly, intersection point also can be handled logarithmic time. So hence overall time complexity is this much. So any questions till now? Okay. Now we will look at the data structures required for the maintain the sweep plan status and the event queue. So on the sweep plan status, what are the operations we are performing? Insert and delete and left off, right off. So if you go back and see, we are finding which is left of this segment in the sweep status, and delete and insert. These are the operations what you are performing on the sweep status. So what data structure is suitable so that all these operations can be done logarithmic time? So all of you listening, what data structure is required for to perform this operation logarithmic time?
Sir, set.
Yes?
Set.
Huh?
Sir, a normal set with.
Normal?
Sir, set like can call it a heap.
Heap. Anybody can answer this question? Are you listening?
Sir, height balanced by BST.
Yeah,
Like,
basically you can use any height balanced binary search tree. Okay. Of course, you can use any one of them, but in this book, what he did is slightly modified, okay, in the sense, okay. Suppose if you take one example here. So in the set tree, intermediate nodes are actually used to for the search path. And the leaf nodes are used to represent the actual data. So basically, these leaf nodes actually keep this track of these line segments. Internal nodes are used to guide the search path. So any internal is the last element in the left subtree. This one. Okay, for this one, and this is the what is two. So it's nothing actually. In this book, you use this data structure like this, but any height balance binary search tree will do. Okay, this is a simple part. Okay, and clear. Any questions here? And second data structure is queue, event queue. So what data structure we use here? We can use any priority queue like a max heap. Since this we are processing this events from top to bottom are based on the y coordinate. Highest y coordinate is the topmost one and which are processed first. So we can use the max heap based on the y coordinates. If these 2 points having the same y coordinate, then we use this x coordinate in left to right order. So this comes before, then this one. So the left to right order we use if they are having the same x coordinate, same y coordinate. Okay, so we can use this binary search tree. Okay, now is this clear? So in the Q, we are extracting the minimum maximum. Okay, it can be in logarithmic time, and we are inserting the intersection points what we encountered during the flight. Okay, insertions can be done in logarithmic time again, so there's no problem with the priority queue. Okay, now is this clear? Now, if you go back to beginning of this Swift-Lane algorithm, we made some assumptions. Okay, like this: endpoints are distinct, and no 3 line segment intersecting at the same intersection point. Or they can be very complicated event also. Maybe more than 3 line segments are intersecting at the same point, and this also may be a bottom end point of some line segment, and this is also a top end point of some other line segment. So this very complicated event. Okay. So what will happen if such a complicated event is there? Since we know this endpoints in the beginning, we can insert these events in the beginning itself in the event queue. But how to handle this event where it is also top end point and it also bottom end point of some other segment? Should we treat them as a 2 different events, or we should treat as a only single event? And if there's also a part of the intersection points, then how you handle this one? How to maintain this as a single event or multiple events? Okay, so we can maintain one single event. Okay, this event E. So let's name them. Okay, so let's say it's SI, SJ, SK. Okay, so this event is bottom end point of SJ and top end point of SM and intersection of SI, SK and SL. So this is in the left to right order. So we maintain all this information with this event itself. So we are maintaining only one event and we are keeping this information. Okay, this event is bottom point of SJ and top end point of SM and intersection of SI, SK, SL. Okay, so initially we know the bottom end point, top end points, and this information can be, we can maintain. So this intersection point we are finding on the fly, okay, and how you insert it. So whenever we encountered, okay, say SK and SL adjacent to each other in the sweep-length status, okay, we check for whether they're intersecting or not. So when they're intersecting, okay, since they are intersecting, so we find the intersection point and check this intersection point is already present in the event queue or not. If already present, in this case it is present, so then simply you update this information. Of course, SI is not there, so we also add that intersection of SK SL also this event here. Okay, so what we're doing actually, so whenever we are inserting an event into the event queue, we are checking whether this event is also present in the event queue or not. If it is already present, so we are not inserting a new event, but is simply updating the information about that event, saying that, okay, this also corresponding to so and so event. Okay, is it clear to everyone? Any questions? Any questions? But there's no questions. Yes. No response for anybody, from anyone.
No questions.
Okay. So at least someone is listening. Okay. So then whatever we are thinking that event queue for maintaining the queue data structure, the priority queue, that max heap, not going to work to check whether given event is already present in the heap data structure or not. So that we cannot do it in logarithmic. Is it possible to do it?
No, sir, not with the heap.
Yeah. So it is not possible with the heap. So what we use a simple binary search tree here also. Okay. So use the binary search tree, height balance binary search tree for the event queue also. And in height balance binary search tree, you can always find out the what is the next event. That is the maximum Y value. Okay. So last element in this binary search tree is the next event. You can always extract that one. Okay. And given a point, whether this point is already present in the queue or not, also you can check it in logarithmic time. If it is not there, we can insert it, no problem, in logarithmic time. If it already present, so we update the information. Okay, this is the new information about this event. Okay, so here the data structure, what is required here is binary search tree here. So if you use the binary search tree, we can do all these operations in logarithmic time. Okay, and such a complicated case also one can handle very easily.
Excuse me, sir.
Yeah.
Sir, I have a question here. How are we going to exactly handle? Like, one thing is for sure that the intersection lines would be flipping their order, but then the top line which is going to come, where it will be there inside the L, like what order? How are we going to handle that event? I didn't get that.
See here, in this case, we are not yet encountered that SI is also part of the intersection point. Because, okay, yeah, sorry. And SI, SI also adjacent each other. Uh, we can say actually they're intersecting at the same point, the one possibility. And if you're treating this open intervals, I mean endpoints not part of the segments, then intersection between SI, SJ we won't consider. So they're not going to intersect. So intersection between SI and SK is not encountered till now. Okay. So how to handle here is whenever this such a situation is there, first what we'll do is we remove these segments for which this is a bottom end point. So first remove this SJ, all the segments for which this is a top end point. Once we remove this one, okay, it may be a top end point of some other segment also. Maybe something like this. So we remove all of them from the sweepland status. Okay. Once we remove this one, we know that actually which are these line segments going to intersect at this one. Okay. Once we remove this one, this SI and SK are adjacent to each other. We can find their intersection point and we can insert that information with this event here. Okay. Of course, not exactly event, but insert actually is because we are removing this event from the event queue, but we can update this information actually. So once we know this, all the line segments going to intersect. Now update and sequence status by swapping these positions. So order here becomes a reverse order. So SL comes here, SK and SI. Then once you update the sequence status by this reverse order of these intersection line segments, then insert, okay, line segments whose top end point is this event. Okay, so this is the way you have to update it.
Yes, sir. I understood, sir.
Okay, so yeah, something like that you have to handle. Okay, of course, when you implement this one, you will see a lot of minor issues actually. Yeah, we are not even considered the horizontal line segment. So if there is a horizontal line segment is there, I already told actually it's a left to right order. So we treat this leftmost endpoint of this segment as a top end point, and this is the bottom end point. Okay, so basically the sweep line is slightly tilted, okay, with small angle, so that it hits the left hand point before the right hand point. Okay, so of course there's no any sweep line as such in this our algorithm or implementation. It's only imaginary line, it is sweeping from the top to bottom. Okay, we can always assume that this sweep line is slightly tilted so that it intersects the left hand point before the bottom end point, right end point of this horizontal line segments. Okay, any questions? See, I am requesting everybody that, okay, please go through this material from the book. I am discussing this book, this computational geometry algorithms and application by Debug and three other authors. Okay, the Springer publication. Please go through this one. Okay, so today I'll stop the class here. Tomorrow I'll take up a new topic. Okay, so if you have any questions, ask. If there's no more this thing, then we'll stop it here.
Excuse me, sir.
Yeah.
Sir, I had another question. How are we going to exactly insert SM? Because it is a top endpoint, then where it is going to exactly come, how will we decide that?
No, see, this information, okay, this is the one single event which is keeping all this information as a part of it. This event is belongs to these things. So when this is the top end point and bottom end point, that information already there before the sequence started. That information is there. But only thing is here is how to update the sequence status.
Yes, sir. Like while inserting SM, then because it is a height balance tree, then what parameter should we be considering? Like how will we distinguish the case where SM is how it is drawn in the diagram with the case when SM is between SK and SI, something like that. Uh, how will we
Basically, how you say that SM is the right of SI.
Yeah, that's what I meant to ask.
See,
Yes.
see that you have to do it. See how you can find out. See, see for example, if you look at these three line segments, these are order SL is comes first, SK next, and SI is next. So here we are able to find out just because these are the initially the opposite direction, opposite order of this initially position. Okay, so whether when you're inserting this one, okay, so you have to take care this is a part of implementation. This comes not only here, in general case also. Okay, see for example, you have to you take this sweep line position is, say for example this one. Okay, sweep line is moving downwards. You take a little bit of epsilon plus, and at this position you calculate where the SM lies. Okay,
Yes, sir, yes. Got
and
it.
you insert. See, this situation arises in normally anywhere actually. See, if you take a sweep line, when you are inserting this one, okay, so you have a one line segment like this, other line segment is like this. In the sweep line status, this is I and J, and the K is inserting. How you know that actually this you are insert between these two? What we are doing is we are simply maintaining SI and SJ in the sweep line status. We are not maintaining these intersection points. So we have a sequence of line segments in the sweep line status. Okay, and where to insert this one? Think about programming point of view, not algorithmic point of view. We have a sequence of line segments, say S1, S2, S3, S4, S5 like this. Now, new segment you had insert, where you insert it, how you find out between which two segments you are going to insert it.
Uh, Earlier, I thought that we would be storing these all intersection points in some hash table kind of thing, and
No,
we can use that.
you cannot maintain these intersection points. When the sweep line moves, these intersection points changes. So when the sweep line is continuously moving, the intersection point continuously moving, changing, it is not possible to maintain. So only thing that's what you have to remember very carefully. You are only maintaining the left to right order of the line segment intersected by the sweep line, but not their intersection point. It is not possible to maintain the intersection points. So we are only maintaining the left to right order. See, for example, S1, S2, S3, S4, and S5. This order, what is maintained as the sweep line status. See, that's what I showed in the diagram also here. Okay, so that order only you maintain. So when the new thing came, say S6 came to picture, then what we do, you look at this y coordinate of this point, and during this search, okay, you see whether the SK is left of this y coordinate or not. If the left side, then you come this side. If you're right, you go this side. So you have to use this, you have to take this segment SK and look at this y coordinate of the top end point and find out the x coordinate on this one, SK. And you have to decide. So every time you have to calculate this intersection point. See, you have to calculate the intersection point, okay, in the set tree. Then you have to go left or right. You are able to follow.
Yes, sir, yes.
Okay. So this is the extra work you have to do it during implementation. See, like this, there are many implementation details are there. So that we are not discussing as a part of algorithm. Even convex or algorithm also, these minor things are actually we are skipping. But when you write a program, then you realize, okay, how much involved these things and how to take care of each and every small cases. You following?
Yes, sir, yes, sir. Got it, sir.
So each and every time, whenever you're doing the search in the sweep line status, you take the y coordinate of the sweep line, current position of sweep line, and you find out this, okay, x coordinate corresponding to the line segment present in the sweep line, and go this do the search path search. Okay, so this is the way you have to do it.
Yes, sir, yes. Got it, sir.
Okay, see, unless you implement it, actually you will not feel the, okay, beauty of this algorithm, okay, and these minor things involved, okay, that also you cannot work out. Okay, we can discuss things at the top level, algorithmic level, but unless you implement it, you cannot, okay, feel the complexity involved in this geometric algorithms. Okay, any other question? So please go through the book. Okay, come to the next class. Okay, see you then.